We're going to start today's lesson by doing some review. So we're going to go ahead and graph the equation y equals x squared and y equals x plus 2. This would be called a system because you're graphing two equations on one coordinate plane. So we're going to graph this system. So we're going to start with y equals x squared, and I'm going to do this graph in black so we can differentiate between the two. So as always, I always put my 0, 0 right here. That's always going to be on x squared. And then if we put 1 in for x, we get 1 out for y. So I always do 0, 0, 1, 1, and 2, 4. And then of course we can mirror those points and we get a nice pretty parabola. So then we change gears and we're going to graph a line. So our y-intercept is 2. And we'll do this one in like an orangish. So we're going to start at 2 and our slope is 1 over 1. And we could continue this trend and then we have our line. So if you recall, solutions means intersections. So wherever the two graphs intersect is called a solution. So if you notice, we have two spots where this occurs. One's right here and one's right here. So we're going to go ahead and say, well, there's two solutions. The first one has the ordered pair -1, 1, and the second one is at 2, 4. So from a graphical standpoint, that's how we can define what solution means. It means the intersection of two graphs. From an algebraic standpoint, a solution means an ordered pair that satisfies an equation. So if we put -1 in for x and 1 in for y, you'll find that this is a true statement. It's also true if you use 2 and 4, right? 4 equals 4, that's true. So these ordered pairs algebraically satisfy this equation. Well, then they would have to over here as well if that's where they intersected. So if you put in 1 and -1 for x and y, you will get 1 equals 1, that's true. And if you put in 4 and 2, you also get a true statement. So that's how you algebraically justify that these are both solutions to these equations. It's quicker though if you think of from a graphical standpoint, those are where the two graphs intersect. So we're going to be doing two different types of systems. The first one is where I will give you a quadratic equation and a linear equation like we just saw. And the second type, I will give you two quadratic equations. Regardless of which type of system you're solving, you're going to get three possible answers. So the first one is no real solution, which means no intersection. So for a type 1 scenario, that could look something like this. You can see physically that they don't intersect. Or if you have two quadratics, you can see, oh yeah, they definitely don't intersect at all. So there's no real solution. You could get one real solution. So we have a graph of a line and a parabola. They intersect one time. It may look like they intersect more, but if we were to zoom in really far on this, you would see there's a tiny bit of space all the way up to here. This is truly where they touch. And if you have two parabolas, kind of same thing. So if you see something like this, it may look like they touch other places, but again, if we zoom in, you'll see that they don't. And then your third type of answer could be, like you saw in the example we just did, two real solutions. So we have a line that cuts through our parabola, or we have two parabolas, one cuts through the other. So for all these systems, you're either going to get no solution, no real solution, one real solution, or two real solutions. And that's how you write your answer. So if there is no intersection, you just simply specify there is no intersection. All right, so we're going to do a little bit of solving here. So we're going to actually use substitution and elimination just like we used them in Algebra 1. So the first thing I like to do is just jot my problem down. And I also have a line of -2x minus 1. The next thing you would do if this was Algebra 1 is you would decide, okay, I either want to get x or y by itself, so pick an equation and isolate a variable. But here's the catch. We can't isolate x in this problem right here, in this quadratic, because you don't just have x, you have x and x squared. So you either isolate the x squared or the x, but you can't do both at once. So as a good rule of thumb, we always solve for y. to help us avoid any confusion or any of that getting stuck stuff that could come up your way. Now y is already isolated, so we can actually just take this whole thing right here and we can substitute it in for y into the other equation. So that's exactly what I'm going to do. Now, since you have a quadratic equation, you have to use a quadratic solving method, which could include square root method, factoring, quadratic formula, or complete the square. It's always a good idea, though, to have this side equal 0. So if I move this 2x over, that makes 0. And if I move this negative 1 over, this also makes 0. So I'm left with 0 equals x squared. And if I square root both sides, I just get 0 for x. So I'm going to get one real answer. Now normally we'd be done, however, now you have to get me y. So you can take this 0 and you can put it into this equation or this equation. Either way, you're going to get negative 1. So 0, negative 1 is your one solution for that problem. All right, so we're going to solve it now using elimination. I just like to show my students both ways. That way, you know, whichever one's your preference, you know how to handle it. So I'm just going to show you how to do it both ways. First thing we're going to do is we're going to stack them. So just be careful. There is no x squared term, so we have to put the negative 2x under the negative 2x, and we have to put the negative 1 underneath the 1. All right, and again, it doesn't make sense to try to get our x's to cancel out because you're still going to have an x squared. So we always want to eliminate the y's. We're focused on the y's. So we can multiply this whole bottom row by negative 1 if we wanted to, and that'll do the trick. So now we have 0. We still have x squared, but now these cancel and these cancel. And we get the same thing that we had before. So you know the answer is going to be 0, negative 1. All right, example 2, we're going to go ahead and again start off with substitution. So I'm going to jot down the problem x squared plus x minus y equals negative 1. And because I know that I want to isolate a variable ahead of time, and more specifically, I want to isolate y, I'm not going to write y minus 4 equals negative x. I'm just going to write y equals positive 4 minus x. I'm going to move that 4 over in my head and save myself some writing. Then we can take our group, just like the previous problem, substitute it in for y, and then we'll write it all out nice and neat. So we're definitely going to need to distribute our negative. And again, it's always good to have this side equal 0 when you're solving a quadratic. So we'll do a little bit of combining like terms here. And we get negative 3. And then it's up to you if you want to use quadratic formula, complete the square. We can try to factor it. It does factor really nicely for us into x minus 1 and x plus 3, which means my answers will either be 1 for x or negative 3 for x. I want to separate these because I still have to go get each one's y. So if I put 1 in for x, I get 3 for y. And if I put negative 3 in for x, I get 7. So this will have two real solutions, and these are the ordered pairs that those graphs would intersect. All right, elimination time. So it's probably a good idea. If you're doing elimination, I like to just get y by itself for both equations, so everything stacks nice and neatly. So for this one, I would have negative y. It would be negative x squared because you subtract it, negative x, and negative 1. And for this one, I do already have y on the left. I have no x squared terms. My negative x is already on the right side. However, this minus 4 needs to come over and be on the right side of the equals, which changes it to positive 4. This is nice because my y's are already set to cancel out. So I can eliminate those. So I have negative x squared, negative 2x, negative 3. I personally like to have positive x squared, so I can divide all of these by negative 1 and change it to x squared plus 2x. Oh, whoops, this should be positive 3. So it will become negative 3, and then we literally have the same scenario as in the previous one. So I'm just going to copy those answers. We got 1 and 3, and negative 3 and 7. So in my next video, we will go through and do a couple more problems, and we'll look at doing 2 quadratics instead of just doing a quadratic and a linear.